Right, so this week we'll finish up vectors, and this is also going to be the end of chapter 8. So in the pre-cal book, chapters 6, I think it was 6, 7, and 8, those are the chapters that covered trig. So after this week, we'll pretty much have covered everything that we're going to do in trig that's new. In the remaining chapters, 9 and 10, there's a little bit of trig in them, but it's nothing new. It's using stuff we already know to do some things. So we're pretty much almost at the end of everything we're going to cover that's new for trig. All right, so last time we left off with this notation, okay, different way to write a vector. And the advantage of writing it this way is that you don't have to draw it. Okay, drawing can be time-consuming, and if you want to do a nice job, you're going to have some kind of ruler or something straight. But we're going to kind of get away from the drawing unless we have a word problem. Okay, that's really the only time that drawing it out is helpful. Okay, so the first thing we're going to look at is when two vectors are equal. Okay, what does it mean for two vectors to be equal to each other? And it's a pretty straightforward idea, but what it means is that the horizontal components match and the vertical components match. That's what it means for two vectors to be equal. So if I drew, let's just put up a grid. Okay, and let's say I drew a vector like that. And I just trace over it. Draw a different one. Are the red and the green vector equal? Yeah. Are they drawn in the same spot? No. So for two vectors to be equal, it doesn't mean they have to be drawn in the same spot. It just means that if you were to measure them, they have the same horizontal and the same vertical component. Basically, if you drew them and put them in the same spot, they'd be right on top of each other. Right? But those two vectors are equal. Okay. Any questions on that? All right. So the final way that we're going to look at writing a vector is in what's called unit vector notation. So first way we did it was visually, we drew it. The second way we did it was with the angle brackets, and this is going to be the third way. Somebody remind me again from last time, what is a unit vector? What does it mean if a vector is a unit vector? Yeah?
One unit long.
It's 1 unit long, yeah. So this notation is going to have something to do with vectors that are 1 unit long. So I want to look at two special unit vectors. Okay? And these vectors are given special names. Okay. And the first one is the unit vector I. Okay? Not the complex number I. It has nothing to do with that at all. Okay? It's the vector I. So you should either try to make it look bold or put an arrow over it. But the unit vector I is defined to be the vector that's 1 unit long. And this one points to the right. That's all it is. Okay, so if you wanted to look at it visually, there's the unit vector I. It's 1 unit long, and it points to the right. Okay, the other special vector we're going to look at is J. So the unit vector J is also 1 unit long, because it's a unit vector, but this one points up. And since right now we're only working in 2D, that's all we need to think about. Okay, there is one more special unit vector, but it only applies if we're going to work in 3D. Okay, and that'll be on Wednesday. Anybody have a guess what the third one is called?
K.
Yeah, it's K. Okay, so I points up, and I points to the right, J points up. Okay, and there's a picture of J. So what I want to do is I want to take those two unit vectors, and I want to think about kind of stacking them together. Okay, and I can make multiple copies of them too, okay, and stack them together to kind of build a vector. Okay, so what I'm going to do is I'm going to give you a vector that's in the form that we used last time, and I want to see if we can build that vector out of i's and j's, okay, by stacking them together. Okay, so I've got the vector 3, 4. Okay, just to make sure we're clear on this, Brad, what's the horizontal component of the vector 3, 4?
4.
No, that's the vertical component.
Yeah.
The 3. So the 3 is the horizontal, the 4 is the vertical. So what that means is I'm going to start at the origin. And what's the name of the vector if I start at the origin?
Position.
I'm drawing a position vector. I'm going to go 3 right and 4 up. Okay, I'm going to draw that vector. Okay, and what I'll do is I'll put that in a different color so it stands out from what we're doing. Okay, so that's the vector 3, 4. Now I want to take i's and j's and stack them together, starting at the origin until I get to the terminal point. Okay, so I'm going to start with the i's, and what I'm going to do is I'm going to make those red, because as I draw them, they're going to be right on top of the axis, so now you'll see them. Okay, how many i's am I going to have to stack together? Yeah, I'm going to need 3 of these i's. There's my second one, and my third one. Okay, so I just used 3 of the i's. And then how many j's am I going to stack onto the end of that?
4.
Yeah, I'm going to stack 4. I can do these in black because you'll be able to see them fine. I think I tilted that one a little bit, so let me just copy it again. And one more time. Okay, so now I'll stack those 4 together. Okay, so we got 1, 2, 3, 4. Okay, so what I basically just did is I built the vector in green by stacking together i's and j's. And this thing that I did, we kind of did this earlier on the first day. What did I really just do with the red arrows and the black arrows? What operation is that? I added them, right? I connected the beginning of one to the end of the other. And then I connected where I start to where I stopped. So really I just added 7 vectors together. 3 i's and 4 j's. So that is the final notation that we can use to write the vector 3, 4. 3i plus 4j. Okay, now, what would be the problem if all you did was use positive I and positive j? What quadrant would you be limited to here? You'd be limited to quadrant 1. You could get anywhere you want in quadrant 1. You could even use a half I if you wanted to go in between, but you'd still be stuck in quadrant 1. What do we have to do to I and j to get into quadrants 2, 3, and 4? Yeah, make them negative. Okay? So if we want to go left, we wouldn't use positive I, we would use negative I. And if we want to go down, instead of using positive j, we could use negative j. So if I had the vector negative 5, 2, okay, that would be in quadrant 2. Anyone think they could tell me how to write that with i's and j's? Yep.
Negative 5i plus 2j.
Yeah, that would be negative 5i plus 2j. We're not normally going to go through stacking all the vectors together to do that. We're just going to look at the vector and be able to write it that way. Right? So you should be familiar with both notations. Okay, so what I'm going to do now is give you formulas for adding, subtracting, a little bit of multiplication, and finding the magnitude using the notation we just came up with. And I'll also do it in the notation we had last week.
How would you find a vector that's like just horizontal?
Okay, so what would happen if you just had a horizontal vector
I would say going to the left.
going to the left? What would that mean?
There's like a negative I component, but no negative j component.
So it would have a negative I component, and can you explain the j component again?
And that would have to be 0.
It would be 0. Yep, so if you have a vector that's on an axis, you'd have a component that's 0. So you could put 0j, or when it's a 0 component, we normally don't write it. We would just write like negative 3i. And that would be it. All right, so the formulas I'm about to give you, anywhere you see a v and a w in the formula, those are vectors. And alpha just represents a scalar. It represents a number. Okay, so there's vector v, okay, written in the format we used before. Okay, if I wanted to write it the new way, I could put x1 I, okay, something I, plus something j. Okay, that's how you write it in the new way. Something I plus something j. Okay, first formula, okay, is for adding vectors together. Okay, I didn't write each formula using the old notation and the new notation. I pretty much just did it with the older notation. The reason I did that is because I think the formula looks a little cleaner. If I use the new notation, there's a lot more letters involved, so it looks more confusing. But the idea is when you want to add vectors, take the horizontal components, add them up. Take the vertical components and add those up. So now this takes the place of all that sketching you had to do by hand. So what I just wrote down, v plus w, takes the place of doing all this. Take that, put that on the end of it, and then draw what's in blue. You don't have to do that anymore. Okay? We're just going to do it using numbers. Nothing visual at all. Okay, anybody think they know what I'm going to do to subtract vectors? What do you think the formula will be for that?
Flip the sign.
Yeah, you just flip the signs, or just you flip the whole thing.
So what do you think I would write? What would I write down?
Is it x2 minus x1?
I think it's x1 minus.
Well, it depends on the order you're subtracting, if we're doing v minus w or w minus v. In this case, it's v minus w. So it would be x1 minus x2. Keep it in the same order. And xy1 minus y2. So now this formula takes the place of when we had to subtract vectors. What did we have to do first when we did it visually? So adding is what I just did with that blue vector. But what if I wanted to subtract this and that? You have to flip the direction of the second one. Right? So you'd have to flip that and then add it, because flipping the direction makes it negative. Okay? So now we don't have to do that anymore if we're going to do it numerically. Okay? Okay, the second one, this is scalar multiplication. So this is the case where one of three things can happen. When you scale a vector, what's one thing that could happen? It gets shorter. Yep. What's another thing? It gets longer. And the third thing?
Reverse.
I could reverse the direction. Yeah. how would the direction reverse? What kind of number would the scalar have to be? Negative. So when you want to scale a vector, it's basically like a distributive property. Multiply the horizontal component by your scalar, and then multiply the vertical component by your scalar. Okay, and the last formula has these double bars around it. What do those double bars mean? It means magnitude. All right, so let's see how we could find the magnitude of a vector. Let's say I had a vector, and I'm going to draw that. Any thoughts on how I could find the length of that vector? Think of it as a line segment. How could you find the length of it?
You could the vertical and horizontal components.
Okay, you could get this is the vertical component, and then this is the horizontal component. Yeah, and then we could just use the Pythagorean theorem. So if the horizontal component, I think I called it x1, at least in the first vector, and that's y1. Okay, all we'd have to do is use the Pythagorean theorem. x1 squared plus y1 squared. You just add those up, and the last thing you have to do is take the square root. Okay, so there's your formula for finding the length of, and I used v. Okay, if you wanted to find the magnitude of w, well, then you'd use the components for w. Did anybody notice something about these two operations compared to the last two? The first two operations are a little different than the last two. There's something very different about them. Anybody see what's different?
It's one vector.
What's one vector?
The times multiplication and division.
So the multiplication, we used a single vector. And what other one?
The division.
Division?
Magnitude.
Magnitude, yeah. The magnitude, we used a single vector. So these last two operations, if you want to scale a vector or find the length of it, you only need one. But if you want to add and subtract vectors, obviously you need two. You can't add one thing. You got to add two things together. All right. All right, so now we've got some actual vectors with numbers. I want to try doing one of each of those operations, and we'll write our answer the new way, okay, with i's and j's, and we can do it the old way with the brackets. All right, so let's start with v plus w. Okay, so remember, the idea is combine the horizontal components and then combine the vertical components. Okay, so Curtis, what would I get here if I combine my horizontal components? And let's do it the new way with i's and j's.
You would get 5i.
Yep, we're going to get 5i. And what about the vertical component?
Would it be 1j?
No, it wouldn't be 1j. What's the vertical component of v? What number? 3. And what's the vertical component of w?
I mean, negative 1j.
Yeah, so when you combine 3 and negative 4, it's negative 1j. Or instead of writing negative 1j, you could just write, you could just put negative j. Okay, so that's the answer in ij notation. Can someone else tell me how I would write it the other way? What would you put, John?
And then negative 1.
Yeah, 5 and then a negative 1. Okay, so any question on how we get that, either the new notation or the old way? Okay, so now let's subtract. Let's try v minus w. Nick, can you tell me my horizontal component when I do v minus w?
It's gonna be 5.
Okay, how'd you get that? What'd you do?
There's a 5 right
A 5. So this, remember, for this answer right here, we're not using that, because that's our answer to part A. We got to go back to what was the original problem. So what's the horizontal number in V? 2. And then the horizontal number in W? 3. Just subtract those two.
Would be -1.
Yeah, -1. And what letter would I put next to it? Not V. V and W are just the names of the vectors. Since that represents the horizontal component, Brad?
It'd be a -9.
Yeah, we put an I next to it. Okay, so -1I or -I. And Ryan, how about my vertical component? What's my vertical component in V? What letter there represents the up and down, the I or the J? The J. So the vertical component in V is 3. And how about in W? No, careful. -4. And when you subtract those two, what do you get? 7. 3 minus -4. So we get plus 7. And what letter would go after that? Yep, J. Okay. So -I plus 7J. Or, Jack, do you think you could tell me the other way? I would write this kind of like the one we did up above.
7 to what? Minus.
So first, what goes before the comma is going to be the coefficient of I. So what number is in front of I?
-1.
Yeah, -1. We didn't write it with IJ notation, but you do have to write it if you're going to use the angle brackets. So we got -1. In Denver, the vertical component, 7. So when we write it with angle brackets, we don't use any letters. Just two numbers between the brackets with a comma. Okay, any question on adding or subtracting? All right, let's take a look at scaling. Austin, what's going to happen here? Just you don't have to give me an exact answer. Just describe how 3V compares to V.
It's going to make it longer.
It's going to make it longer. How many times?
3.
Yeah, it's going to triple each component. It's going to be 3 times as long. How about the direction?
Doesn't affect it.
Yeah, direction will not be affected. Okay, so we've got V, and we're going to triple it. Right, so Jacob, if I triple my horizontal component of V, what would I get? 6. Yep, 6I. So I'm going to start with that. And if I triple the vertical component of V, I get 9. Nope, not I, because it's vertical. J. Right. So 6I plus 9J. And both of them stay positive because we didn't multiply by a negative. Right, so 6I plus 9J. And Fred, could you give that to me in the other format?
6, 9.
Yeah, that's it, 6, 9. Okay, so any questions on scaling a vector? Okay, it's a lot easier than having to do it on paper by drawing it, because if you were going to draw it, you'd have to take your vector and then draw the same thing 3 times. This, you just do multiplication. Okay, and the last one. Ethan, what is that asking me for?
No idea.
Those double bars? Not sure? Anybody help them out? What do those double bars mean? Magnitude. What's magnitude really mean? Can you give me a simpler word in case anyone's still confused? Length. Okay, we're trying to find the length of it. So the idea here is we basically use what theorem? Yeah, we use the Pythagorean theorem. So we take each component, we square them, add them up, and then take the square root. All right, so how about Alex? We're finding the length of V, so we don't need W at all. What's the first number that I'm going to square?
Should be 2.
2, and the second number I'm going to square
There's 3.
is the 3. So I'm going to do 2 squared plus 3 squared. So it's going to give me 4 plus 9. And Sam, if I add those up, that's the square root of?
5.
Careful, you subtracted them. You want to add them. So let's do it step by step. What's 2 squared?
It's 4.
4. And 3 squared?
9.
9. 13. Okay, so you get the square root of 13. If they don't ask for a decimal, you can leave it just like that. If you ended up with something like this, which we didn't in this problem, but what would you have to do with square root 20? You'd have to simplify it, okay, into like 2 square roots of 5. Okay, 13's prime, so you can't simplify that. Okay. So any question on finding the magnitude? Okay. Does anybody need any of the formulas on the other page again? Make sure you've got your plus sign, not a minus, things like that. Okay. And these are also all in your packet. Okay, if you look, well, it's last week's packet. Okay. But there's a box in the packet, and I think all those formulas are in the box. All right, so next thing we're going to look at is how can we take a vector that we're given and turn it into a unit vector. Okay, so just as a reminder what a unit vector is, if the length of a vector is 1 unit long, then it's a unit vector. So if I have a vector that's too long and I want to turn it into a unit vector, what that means is I don't want to change the direction of it. I only want to do one thing. If it's too long, what would I have to do to it to make it a unit vector? I'd have to scale it down. What would I scale it down by? Well, depends on how long it is. If it's 2 units long, I'd have to scale it down by a half, make it 1 unit long. What if I had a vector that was 5 units long? What would you have to scale that down by to make it 1 unit? Careful, negative would flip the direction. Yep, 1/5. If you have something 5 units long and you make it 1/5 as long, it's 1 unit. What about if you had something 8 units long? 1/8. What about if you had something x units long?
X minus 1.
1 over x. So that's the pattern. You basically scale it by 1 over its length. Okay? So to find a unit vector, okay, if you're given a vector, what you have to do is take the vector and scale it by putting its length in the bottom. Okay, doing this is exactly the same as this. This is what you guys said to me. Scale the vector by 1 over its length. Well, 1 over its length is exactly the same as dividing by its length. It's like saying divide by 3 or multiply by 1/3. It's the same thing. Okay, so that's how you can turn a vector into a unit vector. Okay, so step 1 is find out how long is your vector. If it's already 1 unit, don't worry about it. It's already a unit vector. If it's not, you're going to have to scale it. And you always scale it by 1 over its length. or that's the same as saying divide the vector by its length. Hey, any questions on that idea? Even if a vector was too short, this formula would still work. If you had a vector that was too short, you could still use the same formula and it would make it long enough to make it a unit vector. Okay, so always scale the vector by 1 over its length. All right, so I've got the vector 3i minus 4j, and it says find the unit vector. Okay, in order to do that, what's the first thing I have to know about 3i minus 4j? If I want to find a unit vector for it, what do I have to know first? I got to know its magnitude. Maybe it already is a unit vector. I don't have to do anything. But it's probably not. So I got to find its magnitude, and then I can use that in the formula. Okay, let's find the magnitude of v. Hey, Bria, can you set up my expression that I'm going to use to find the length of v? Mm-hmm. Yeah, it's always plus, because think of Pythagorean theorem, right? You're always adding. So plus negative 4 squared, and take the square root. And if I add 3 squared and negative 4 squared, what's that going to give me? 25. So that means the length of this vector is 5. Is it a unit vector? No, it's too big. So what am I going to scale the vector by? I'm going to scale it by 1/5, which basically means you're going to divide each component by 5. So here's my scale factor. Okay, 1/5 times my vector. And what do you basically do with this 1/5? Yeah, it's like distributing it. So what's 1/5 times 3? 3/5. And what about 1/5 times negative 4? Negative 4/5. So as I pointed out earlier, it's basically like I just took each component and divided them by their length, by 5. So this is a vector that points exactly the same way as the original. I didn't do anything to change direction. I just shortened it by 1/5. Okay? And you could try Pythagorean theorem on this and check it, and you could see that it would be exactly 1 unit long. Okay? If I did Pythagorean theorem, that's 9/25. If I square that, that's 16/25. And what's 9 plus 16? So the length of this vector is the square root of 25 over 25, which is 1. So it is exactly 1 unit long. Okay, so any questions on that? Okay, so step 1, find the length. Step 2, scale the vector by what? By 1 over that. Okay, and that'll make it exactly into a unit vector. All right, so last thing we're going to look at is a word problem. Okay, and it's going to have to do with velocity. So we said earlier we can use vectors to represent the speed and direction of an object. I might have shown you something with all the airplanes. I'm not sure if we did that in here, but did I show you that on the board? Yeah. So we had that map of all the different airplanes, and I said you could think of each vector, each airplane as a vector. It has a direction, and it has a speed. The thing that's complicated about airplanes a little bit is it's 3D, so they also have an altitude. So, but we're just working in 2D. So if you can come up with a a vector that represents the speed and direction of an object. That's called a velocity vector. Okay, and that's what we're going to try to come up with next. All right, so first we've got to figure out the formula for a velocity vector. Okay, when I write a vector like this, what's that part that I just pointed to? Yeah, that's the horizontal component. And what about the second part I just pointed to? That's the vertical component. So the goal is basically find the components of that. Which, if I wanted to make a shape to help me do this, what shape would I turn that diagram into? I'm going to turn it into a right triangle. So I'm just going to use this line as a guide for a second. And my horizontal component is right there. It's kind of hard to see, but it's there. And my vertical component is right there. Okay, I need to find the blue and the red arrows. Okay, and that's what would go in those two spots. So when you're describing a velocity, let's say you're describing like an airplane flying. Does anyone know how they usually describe an airplane flying? What two things would you have to say about the plane? Assuming it's just staying at the same altitude. And you wanted to know exactly the direction, how it's traveling. What do you need to know? You need its heading, which is usually, what's a heading?
Which way it's going.
And can you give me an example of a heading? Same on a boat too, they use headings. What's a heading? Like what is that?
The compass direction.
It's a compass direction. It's an angle, right? So the two things you'd have to know is the angle, okay, that it's traveling at, and the other thing you'd have to know is what else? We don't have to know how far it's traveling if we just want to know how it's moving right now. We have to know the direction it's going and the speed. Okay, that's the two things we need. Now, the speed is really the magnitude of that vector. Okay? That's what I need to know. Okay? I don't need the vector, I need its magnitude. That's the speed. All right, so let me just look up the letters that I use. All right, so. All right, so let's temporarily, we'll just call this x and y. Okay, we're going to know what x and y are in a second. And that's a right angle. Okay, what trig function would I use that would involve this side, and that side? Careful, tangent doesn't have hypotenuse in it. Well, what two sides are we dealing with? X is what side? It's adjacent. And then I just said the magnitude of the vector is the length of the hypotenuse. And what trig function is that? Cosine. So the cosine of that angle equals adjacent over, and it's important here that you don't put v. You have to put the magnitude of v, because that's its length. And how would we get x by itself? So I have a formula for the horizontal component. Multiply each side by the magnitude of v. There's a formula that'll tell you the horizontal component of your velocity vector. All right? And did anyone have a guess what y is going to be without setting the whole thing up again? Yeah, it's going to use sine. So what would your formula for y be?
The magnitude of the sine theta.
Yeah, it's just going to involve two different sides. It's going to involve opposite and hypotenuse instead of adjacent and hypotenuse. And that's your horizontal component. Horizontal, vertical. Basically, just plug those two things in where those two arrows are, and that's your answer. Okay, so let's look at it. So the formula that I'm about to give you, you have to know two things to use it. One, what's the initial speed of the object? Okay? That's the magnitude of v. That's the speed. Okay? The other thing you have to know is what is the angle that the object is traveling at or being thrown at or launched at, whatever it is. That's theta. Okay? So magnitude of v, that's initial speed. Theta, that's the angle that it's being thrown at. For our purposes, we're going to measure the angle with the horizontal. That is not how a compass works. We would call that like a 40-degree angle. Okay, the way a compass, well, and what if I threw something like that? What angle would that be? That would be a 0-degree angle. On a compass, when you go to the right, it's not 0. It's 90. 0 is north on a compass. Okay, so how you measure the angle is a little different than how we're doing it, using a compass versus what we're doing, but it's still the same formula. Okay, we're just calling right 0. We would call 90 up. Okay, 180 would be left. And yeah, that's pretty much all we need. Okay, so there's our formula. Okay, now I didn't write it the old way. I just wrote it the new way. Okay. Horizontal component, cosine of your angle I, and then it would be plus your vertical component times sine of your angle j. But what does this and that both have in common? The magnitude of v, and that's why I factored it out and put it in front. So all you're left with is cosine angle I plus sine angle j. You can call the angle whatever you want. I think the book might call it alpha. I used theta. It doesn't matter. Just think of it as cosine angle I, sine angle j, with the magnitude factored out in front. Okay, so alpha in this case is the angle you throw it at. V is the initial velocity. Okay, so we're really simplifying this. We're not taking into account different things that could happen. For example, when you throw an object, it's generally going to slow down the second it leaves your hand, okay, because of air friction and things like that. For our purposes, we're just going to use this simple formula, which doesn't really take into account all that advanced stuff. So the formulas that we're using would work pretty well if you were doing it in a vacuum without air friction. Okay, but that's not realistic. But it makes it easier. All right, so we're going to throw an object at 50 miles an hour at an angle of 30 degrees. Okay, so the first step is just find the velocity vector. Okay, so we got to start with our initial speed. Denver, what's my initial speed here? 50 miles an hour. That is going to take the place of this. So fill in 50. Parentheses. What trig function comes next? cosine. And now it's the cosine of my angle. And that's going to be the I component. What's the angle I'm throwing it at? 30. Plus, and then what's my other trig function? Sine of what's the angle? 30. And what component is that? That's the vertical for J. Now, to write this and kind of do it out, what do you think we have to do with the 50? Yeah, we have to distribute it. Okay, so on our calculator, we'll type in 50 cosine 30. Okay, we get about 43.30. And someone remind me again, what component is that? That's I. Plus, now do 50 times the sine of 30. And that's going to give us 25J. Okay, and that's the velocity vector. Okay, now the second thing they asked us to do is explain the meaning of each component. Okay, well, we know that's the horizontal component, and that's the vertical component, but what does that really mean in this problem? Let's see. Anyone think they can tell me what either one of these numbers has to do with throwing an object at 50 miles an hour at an angle of 30 degrees? What are these two numbers? Brad? Okay, what do you mean by separate speeds?
That's the 43.3, that's the horizontal speed throw it at.
Yep, that's your horizontal speed.
Miles per hour, and then 25 is the vertical speed that it goes.
That's your vertical
We
speed.
did stuff like this in physics.
So in other words, if you were like, pretend like you were right in front of me and you were throwing the ball to me. Yeah, I had a radar gun, right? And I pointed it right at the ball coming straight at me. This is what the radar gun would say. It's coming at me horizontally at 43.3 miles an hour. Okay? If I was up above the ball, okay, let's say I was like 100 feet up in the air and I pointed a radar gun straight down at the ball, the radar gun would say the ball is coming up at the radar gun at about 25 miles an hour. Okay? So those are the two different speeds. Yeah?
Does it, then initially, because, like, you know what I mean, is this the initial?
These are initial speeds, yes. Now,
So it's gonna slow down.
only one of these speeds is affected by gravity. Which one of these speeds is affected by gravity? Only the vertical. So the vertical speed is constantly changing. The second the ball leaves your hand, okay, the vertical speed is slowing down. Okay? The horizontal speed is really only affected by one thing, not gravity at all. Why would the ball slow down horizontally? Because of air friction. If there was no air friction, the horizontal speed would stay exactly the same the whole time. Okay?
Or ground friction.
And then, knowing these two speeds, in physics you can figure out other things. Like, if you throw an object up at 25 miles an hour, how high does it go? How long is it in the air for? Things like that. Okay? But for our purposes, we're just figuring out the two speeds. Okay, so any question on finding a velocity vector? It really just uses sine and cosine. Okay, so the homework tonight, okay, it's in your packet from last week. Okay, the packet I gave you today starts on page 346. This is 344. Okay, 25 to 47 odd, and 55 and 57. Yes? From last week? All right. I'll see. I probably have another one.